The video, we're going to talk about the curve on a surface theorem. Now, what is the claim? Well, let phi be a k-chart mapping some subset of the k-dimensional real space into the n-dimensional real space. So let phi be a k-chart and some curve C mapping the interval I as a subset of the real number line onto the surface phi u be a non-singular, meaning that it is not equal to the zero vector anywhere, or its derivative isn't, rather. Parameterized curve on some simple k surface the k surface being simple, it simply means that it can be described with a single chart, right? For example, take the sphere. The sphere may not be, and this is a non-trivial result by the way, may not be described with a single map. Its atlas needs to be larger. I believe at least 3 maps. Or 2, I'm not sure. I'm sure now. Definitely more than 1 though. So that's not a simple surface, but this is a simple surface, meaning it can be described with just one chart. Simple k surface phi u. Then u defined as phi inverse after c, which maps the real number line onto u, is a non-singular parameterized curve in U, and it holds that C, the curve, can be described as the composition of phi and U, right? So perhaps a picture is in order. Well, let's do our best to sketch this. So we have k-dimensional real space U down here. Somewhere up here we have a simple surface like so. And between them we have the k-chart phi. Right, here on the side we have the interval I. This is phi of u, right? And some curve C mapping this interval onto the surface. Right, so we have some curve C here. Right, and finally we find some map U, which takes the interval I, maps it here onto C, and then this is mapped down here back to U. So we have a last map mapping the interval I down here. And now we claim that C, so this curve, can be obtained by mapping the interval I down here into the U space and then raising it up with phi up here, and that is the same thing. Right, now let us have a look at the proof. Well, we observe that U is a continuous map. Why? Well, here we have the definition of U, and as we can observe, C is continuous. It is in fact smooth because it is a curve. We only consider smooth curves. And phi is a chart, meaning that it is a homeomorphism, and as such it has a continuous inverse. So U as a composition of two continuous functions is continuous. Moving on, we would like to know, so we wish to find out if, or we wish to determine rather, if if U is also continuous. So if it belongs to, if it is a member of the class C1, if it is smooth. Well, we know it is continuous, we are asking if it is smooth. Well, we should now put some definitions. So put, and we have let T be some element of the interval I. So let T0 be up here. Then we denote x0 as the image of this under C. So T0 will be mapped somewhere here to be x0. Right? Let's write it down formally. So x0 we put as the image of T0 under C. And finally U0 we define as the inverse of phi of x0, right? So in the picture we put it somewhere down here. We put U0. Right, finally we define pi to be some projection, projecting the n-dimensional real space into the k-dimensional real space. And we put G as the composition of this projection after phi, right? So here in the picture we would have another plane, rather I'm out of space. Okay, put another picture here, and this would be the surface after applying the projection pi. So this would be pi of phi of U, and we can denote G to be a function mapping U here. Okay, now without any loss of generalization and without any loss of generality, we know the rank of the Jacobian of phi at U is k, because phi is a k-chart. Without any loss of generality, assume that we needn't shift anything about, that the first k by k submatrix of this Jacobian is non-singular. Okay. Now, since, this means, by the way, that the Jacobian of dj, or dg, the Jacobian of g at u0 is non-singular. Why? Because this is precisely this. It is the first k by k submatrix of this larger Jacobian. They are the same because G is defined as phi composed with the projection pi. Now, because everything is smooth and beautiful and continuous, we can invoke the local diffomorphism theorem. Local diffomorphism theorem. And this one tells us that there must exist the inverse of G on some, restricted to some neighborhood of, and we can choose any point we like, because here we wrote G of U0, it would be nice of us to choose some V0 from from this plane, which we can dub V, and we will put this V0 equal, so where V0 is equal to pi of x0, but also this is equal to G of U0. Right, so here's the connection. Okay, it's all nice and well, but, oh, I didn't finish the sentence, on which G is a diffeomorphism. This is a needfully strong notion for our case, but it will do, because since it is a diffeomorphism, it is a two-way differentiable isomorphism. As such, the inverse exists, so we can write G inverse after pi as which then, if everything is well defined, we write that this is actually equal to phi inverse, which we know that exists since phi is a homeomorphism, on phi of u, where u is the set, phi of u intersected with pi inverse, the preimage of pi. Of course, defining an inverse on a projection will be problematic, but we say the preimage of v under pi. And this means then that we can safely define u as phi inverse after c, since all we need to do is to take this expression, which we already know is well defined, put it here, G inverse after pi, and compose it with C. And we know that this works on some neighborhood of t0. Why t0? Because we want to feed pi x0, and of course C of t0 is x0. Right, but this means then that u is smooth. U is smooth. So the diffeomorphism wasn't too strong a notion after all. Why is it a diffeomorphism? Well, that's because... Well, why is it smooth? Well, because C is smooth, pi is smooth, and G inverse is a diffeomorphism, and therefore, well, G is a diffeomorphism, and therefore G inverse is smooth. And U is thus a composition of three smooth functions, and as such is smooth. Now, moreover, we have demonstrated that indeed this interval is mapping, or rather is mapped by C here by definition, but also, that is what we have demonstrated, that the function U also maps this interval onto this function. This follows trivially from the fact that we put U as this, and thus if we compose both sides with phi from the left, we get that phi composed with U is equal to phi composed with phi inverse composed with C, which of course is simply C, which is the equality we wanted. So we have demonstrated that it is a curve and that it maps the points where they belong, along with some neighborhood for each point, which is precisely what we wanted, and this concludes the proof.